So it is my pleasure to introduce the first speaker of the morning session, which is H.Briegel from Innsbruck and Constance, who will be talking about learning and AI in the quantum domain. So a very general title for a researcher who has done many, many things. So please, Hans, take it away.
Thank you, Vedran. So let me first try to do that. So can you see a slide with the title Learning and AI in the Quantum Domain?
We can.
And you can see the pointer as well moving?
Yes.
Can you see the pointer? Okay. Very good. Okay, so thank you very much for the invitation. I would have preferred to come to Tübingen in person, but this is an interesting experience as well. So let's try to go with this. So this is research. I'm reporting about research we have done the last few years with a group of people in Innsbruck and in Constance. And the broad topic is learning and AI in the quantum domain. So let me first introduce myself. So I'm a physicist. My background is in the field of quantum information and computation. And I'm not exactly sure about your backgrounds, but the quantum information community, so this field deals with the enhanced possibilities of information processing when you encode information in the states of quantum mechanical systems, as Bert has highlighted in the introductory words. So if you encode information in atoms and photons and so on. And the slogan "information is physical" has been a guiding motto for our field, which then implied that the ultimate scope and power of computers and any kind of information processing must be determined by the laws of physics. So from the perspective of theoretical physics, the research on fundamental concepts of quantum theory, such as complementarity, indeterminism, entanglement, is what drives us towards computation. We would like to understand these basic notions in view of novel applications, such as an increased level of efficiency for computers, security in quantum cryptography, and reduction in quantum simulation. Now, more recently, people have started to investigate the implications of quantum physics for machine learning and AI, and the other way around. And you may wonder why this has taken so long, because machine learning and computing is of course closely connected, and there are various reasons for that. But in any case, the study of these interplay of these concepts is really the topic of the broadly defined field of quantum machine learning. It deals with the mutual interplay of concepts and techniques from quantum information on one side and machine learning and AI on the other side. Now, one reason I would say why the attention within the quantum community has been increasing, of course, is a general one, and that is the recent series of successes in the application of machine learning techniques. Most notably, for example, DeepMind's AlphaGo, which you all know about. Now, what I find very interesting, this is beyond quantum information, is the important question how this AI summer, let me call it, or revolution, will affect basic research in the future, and how our laboratories, like our quantum computing laboratories, will look 20 years from now. It's not so clear what will be the level of automatization, which machine learning technologies will be used. Will we have something like autonomous lab assistance systems? And what will it mean for the very notion of experiment even? And I will come back to these questions at the end of this talk, which really is about some collaboration with philosophers at Constance University. So many of the existing investigations and works in the field of quantum machine learning have to do with machine learning tasks in the sense of data classification, pattern recognition, optimization. There are many interesting papers there. They are very important and exciting developments. The main focus of this talk is different. It is also the main focus of my more recent research. It is more on online scenarios or active learning scenarios, where you have an agent that is a physical entity that learns via interaction with its environment in order to achieve a certain goal, or in order to get around and learn how to best respond to a changing environmental situation. So the key words here is adaptivity, flexibility, reinforcement learning. So the entire focus of my research and my colleagues is it's action-oriented. So this physical interaction perspective is particularly relevant also, of course, in robotics, in what we call explorative experimenting, and even in quantum foundations. And in all of these fields, there's some topic that binds them together, and all of them need a non-trivial notion of agency. And the interplay between agency and artificial intelligence, that's really the main focus of my interest. Now, a general platform to discuss concepts of AI is, as you know, the notion of artificial agents, as you find them, for example, in textbooks like in Russell and Norvig. And agents are described there as entities. They're always situated in an environment on which they can act, thereby changing it, and which reacts in the form of perceptual input. I think an important difference to the notion of a computer is the intrinsic relation of the agent with its environment. So notions of learning and intelligence usually involve the entire interaction history of the agent with its environment, which changes over time the internal structure of the agent. This is a perspective that is a lot emphasized in the field of robotics and also in embodied AI. Now, interestingly, existing schemes of quantum information processing, such as measurement-based quantum computation or quantum error correction, can in fact be viewed as simple agents, since there's a strongly interactive component. So in measurement-based computation, the computational process goes in rounds where a simple device, which I now call an agent, acts on a quantum system, makes a measurement, gets a result, which you can be interpreted as new perceptual input, and depending on the outcome of this measurement, it will make a new measurement. So this is a strongly interactive model of quantum computing, which bears some similarity to an agent. Of course, there's not much learning in there, but you can make it more and more a learning model. And that is, in fact, this perspective coming from quantum information and quantum computation has also influenced the recent work of my group in quantum information towards a general framework for quantum machine learning and AI. And some of this is described in this review article by Vedran, the chairman, and myself in this paper. Now, I will say a little more about the general framework of quantum machine learning shortly, but the focus of this talk will specifically lie on a physical model of deliberation and learning for artificial agents that we have developed over the last few years. And that is a model, it's a new learning model that connects my research both with AI, but also with the broader problem of agency, of artificial agency that I have been describing and that I've become interested. So the model is called projective simulation. I will explain it. And we call it a physical model insofar, so to speak, as the program of the agent, standard terminology of, say, Russell and Norvig, is here replaced by a dynamic stochastic process inside the agent. And it's conceptually, I would say, more similar to the random motion of a particle in a diffusion process than it is to the information processing of explicit data structures in a computer. And as such, it turns out, it also offers a natural route for quantization. Yeah, so this is a model for memory, learning, which can also be quantized at the same time. Okay, so after these introductory words, I will now briefly discuss the notion of quantum agents and the question in which ways quantum physics may enter into the picture of agents, broadly speaking. I will then present an agent model based on the notion of projective simulation and discuss various applications. After this, I will show that this model offers a natural route for quantization, and I discuss the steps towards the model of quantum projective simulation, for which one can show a speed up. And in the second part of the talk, if there's time, I will discuss some more philosophical issues related to this research, and that discusses the I think, the broader scope of machine learning for basic research, and in fact, the very meaning of scientific experiment, if one takes into account this ongoing development. Okay, so now having introduced the framework of artificial learning agents, if you ask the question, how should we quantize that framework, you see several possibilities. Yeah. Broadly speaking, you know, there are two parts. There are two parts here. Here is the agent proper, the device, and here is the environment. And the agent acts, and it gets percept from the environment. So a broad classification of scenarios would be CC, CQ, QC, QQ, referring to, or depending on whether you quantize the agent or the environment or both. So for example, QC would be a quantum agent operating on a classical environment. Something you could imagine like a robot that operates in an everyday environment, but that has a quantum chip inside. And you may be interested in finding out what are the consequences of such a design. How would you notice from the outside? What would be the benefit of it? Or CQ, this one here would be a classical agent operating in a quantum environment, like machine learning, any kind of machine learning methodology in the context of quantum experiments and quantum protocols. Or finally, QQ would be a fully quantized scenario where you have, for example, a quantum computer interacting with a quantum experiment. Here, really fundamental issues about learning and the very notion of an agent and observer come back to us, and it's very interesting fundamental stuff. And there's a recent paper by Vedran Dunchko, Jake Taylor, and myself that talks about these broad classifications and what can be expected in these schemes, and specifically talks about the notion of reinforcement learning in the QQ scenario. I might come back to this later in the talk, but let me now start. I will basically talk about all of these classes, but the most of it, I will first talk about this CC scenario. So that is this model of projective simulation I mentioned. And it's a model where the agent is equipped with a specific type of memory, which we called episodic and compositional memory, with the help of which the agent simulates its actions and its expected consequences by a random walk through a network of so-called clips. Now, clips are the basic units of this type of memory, and in the simplest form, they are remembered percepts or remembered actions or certain combinations thereof. So if you, broadly speaking, you could look at it as a sort of graphical model where edges encode transition probabilities and vertices have a special semantics, episodes. Now, I would consider PS as a simple agency model that has two components. One component is the internal deliberation, or decision finding, which describes how decisions are made based on past experience. The other component is learning, which is here realized by two components. One is the change of the hopping probabilities between these clips. This is the reinforcement part. And B, by the change of the network topology by adding or removing clips. Okay, so I will not have time to go into all details of this, but I have two formal slides that I would like to show before I go into applications in the quantum context. So there is always an external view and an internal view on agents. Externally, the behavior of an agent at, say, time step t is summarized by the conditional probability to do action A given percept S. So that is the so-called policy that changes over time. And if you have a learning agent, typically this is a rather flat distribution initially, and the agent doesn't know what to do in various, for different states or percepts, but over time it learns what is the right action to be done given a certain percept. Internally, from an internal view, a given percept will call with a certain probability a clip from the memory set, from which a random walk will start through clip space, described by some stochastic process, which is in the simplest case a Markov chain, until it will hit a designated so-called action clip, which encodes remembered actions, so to speak, where it will couple out with a certain probability and to do a real action in the environment. Okay, so percepts here can have different categories like shape, color, size, and so on. Actions can also have different categories. It can be various actions, say, of a motors of a robot. It can be a beeper. It can be whatever. Then as far as the reinforcement part of the model is concerned, there is, most important thing is there's a probability rule and there's a learning rule. So the hopping probabilities in this clip network are determined by real valued weights, H values, so we call them, which are associated with the edges, which change after every interaction with the environment based on some update rule. The way they change is defined by some learning rule, and there's a family of those. The simplest learning rule is written here, and that is, for physicists, maybe the best way to describe it is a kind of a discrete master equation, where the weight at time step t1 is given by the weight at time step t minus a loss term plus a gain term. Yeah. So there, the loss term includes a damping parameter that allows the agent to forget over time its past experience, kind of a dissipational process, which is in fact useful when the environment changes. So the agent can relearn and forget old wrong stuff. Lambda is a term that measures the reward. And in this gain term, there is also a quantity which we call glow. So the function G describes the glow status of a transition in the memory. And that is relevant for delayed rewards. So when a reward from the environment is a consequence of series of actions, the glow is something that allows the agent to backtrack and weight how important earlier decisions were in finding or achieving a certain goal. So, it's a memory model, and you can imagine that if you imagine these edges in the graph to be some physical things, then you can imagine that all the time, all edges glow more or less, depending on how long it has been since the transition was taken last time in some decision-making process. If an action is rewarded, the edges that were used in finding this action will be strengthened according to how much they still glow. Thereby, you have different glow status here, and this allows you to backtrack relevance of earlier decisions made in the future. Now, in the following, I will give a series of applications that we have studied this model in detail in various ways. First, we compared it, of course, to standard reinforcement learning. If we look at the model as a reinforcement learning model, we compared it to other models and see how it performs. But when we applied it in real world and practical applications. So the first application is, I would call, just textbook problems. I will not say much about it. Here we summarize some basic textbook style problems that you find in textbooks, where we have tested the performance of the model. So these are all something like simple computer games, invasion game that we invented ourselves, the mountain car problem, the grid world problem. People have also applied it to games like Super Mario. And the main result of these studies that are really summarized in a recent paper in this journal is a benchmarking compared to Q-learning and SALSA, where the upshot is that PS, as we have introduced it, it can compete with other basic reinforcement learning models, at least for these simple applications. In some cases, it performs a little worse, doesn't find quite the optimal path, but in some cases, it's better. The main difference, I would say, is the optimization of the model parameters, which in PS is easier. It's easier and typically requires 1 to 2 orders of magnitudes fewer agents. So if you have an environment you would like to test, this is a model where you can quickly optimize parameters to see how the agent performs. The main part of these investigations was really to show that the model is not completely out of range when compared to established reinforcement learning models. The focus of the PS was not to be a reinforcement learning model only, but it's a model for memory and deliberation of an agent, which can also be used for learning. And importantly, it's a model, as we have shown, that can be quantized. So we just wanted to make sure that it also is competitive and in a comparable range with existing methodology. there is also a notion of clip composition in PS that I haven't much talked about and don't have much time to talk about it. It's a mechanism where new clips in the memory can be created out of existing ones under certain syntactic rules. So an example where clip composition can be useful is in the context of generalization, as we have shown in that recent paper here. Newly created clips in this context are wildcard clips, where some of the percept categories are masked, which allows then an agent to learn relevant properties like color is relevant or shape is relevant of a certain object in a reinforcement learning scenario, like car driving. Another example where composition plays a role is in the context of action composition that was later used also in robotics, where an agent can create new action clips out of existing ones, which is really useful in learning in large action spaces, where you have a combinatorial explosion of action possibilities. If you have n motors for a robot, for example, then how do you switch them on and off, and how do you combine them? I cannot go into much detail here, but I will come back briefly to that in the application. Maybe one last theoretical slide. So I would like to emphasize a different focus between standard reinforcement learning and PS. In reinforcement learning, the focus lies on the environment in which an agent operates, usually described as a Markov decision process. And the goal of the agent, first, a reinforcement learning agent has an explicit goal. That's one of the distinguishing properties, and it is to find a solution to the MDP. That is a policy that maximizes the long-term expected return starting from any state S, and so on. Now, in PS, the focus is different. It is a simpler model, and the focus lies on the memory of the agent and on the internal structures for decision finding, which are described in our case as a clip network. If we do put PS in an environment described by a specific MDP, we are interested not only in how well and fast the agent learns the optimal policy in the MDP and how the MDP will look, how it will be reflected in the clip network here. We are also and often more interested in the question how the structure of the memory develops as the agent learns and how these changes affect the agent's general behavior. We have studied in other works and notions of concept formation and any signatures of agency this device may exhibit. That is really the focus, but it is of course very close to the reinforcement learning. Okay, so now this next application is in a more advanced. So we are collaborating with people in robotics, specifically with a group of Justus Piata, who work on artificial intelligence and applications in robotics. And they use PS in the context of robotic playing and complex skill learning, where a robot has to learn how to grasp and successfully manipulate different objects. So this can be pretty complicated and time-consuming to teach such a robot how to handle objects like books and to put them in a shelf. And PS here is part of a large architecture, which includes, for example, object classification through haptic sensory input. But PS is there used for the part of autonomous playing with the objects, which then, as they showed in that paper here, significantly reduced the cost of supervised learning. This was very recently extended to environments with multiple tasks, where the robot, this includes book grasping, placing objects into a box, placing it into a shelf, aligning it, assembling, disassembling a tower of objects. And for such an environment, a form of action composition that I just mentioned before was in fact implemented, which can become crucial when the number of possible situations the robot can encounter grows larger and larger. So I would like just to, this is still classical, like to draw your attention to these works before I now come to the first real quantum application. So here, the broader question is, of course, that we all have is, can machines be used for the automated design of experiments? Can they, play a non-trivial part? Now, a specific task in the paper that I'm going to present was to design an experiment that produces entangled states of a certain type, namely high-dimensional orbital angular momentum states of photons. This is work that was, forwarded by and presented by a group in Vienna, Anton Zeilinger, Mario Gren, and collaborators, in a very interesting paper. And so let me first say something about the background. These high dimension entangled states are states of at least 3 photons, or systems in general. And in addition, the Hilbert space dimension of each system must be at least 3. So entangled states, as you know, are resources for various applications, such as teleportation or quantum computing, so they are considered interesting in my community. Formally, you classify them by something called Schmidt rank vector. And that will be also then a measure that will be used to create feedback for the automated experiment. Now, given a toolbox of basic optical experiment, the group, were interested in creating such states with high Schmidt rank vectors of many parties and high numbers here in an optical setup. And it was not clear. It was not straightforward to do that. It wasn't clear which of these states could be created. And it was no good intuition, as I was told. So the authors, in particular Mario Krem, wrote a computer program. They call it Melvin, which was at the time basically a search through random configurations of optical elements on the table. And Melvin found new and interesting states. So that is described in this paper here. And this demonstrated that automated search can be very helpful when systems and setups get too complex for human intuition, as we have also seen, in other chess playing, Deep Blue, and so on. Now, we then joined forces so we applied PS to this experiment, where we then really have a more developed notion of memory, episodic memory, and reinforcement learning. So here the available actions were to put certain optical elements on the table, like beam splitters or certain Dove prisms, holograms, and so on. And the percepts that the agent perceived was the current configuration of the optical setup. So there was an interaction going on. Agent puts something on the table. It registers the new setup, and then it's tested whether this setup produces as designated output ports a signal that is in a desired entanglement class. It's not a full specification of one unique state, but it's a broad classification of entanglement. Did you find an example of an entangled state of that Schmidt rank class? Okay, and so the key step in this work where the reference was given a few slides ago, was that the design of such experiments could be mapped to the grid world problem, or a generalized version of this. Here it was.
We're now at 27 minutes.
Okay, so I tried to speed up. So the navigation here was in a complex network instead of a 2-dimensional maze. And I think the key finding, I have to speed up, the key finding was that the agent using PS, in fact, find many more entangled states, and it automatically delivers compact experimental setups. So there was a clear benefit of reinforcement learning. You can go to bigger spaces and find short paths. So the output is an experimental setup that produces a certain class. And it also exhibited some form of transfer learning. So if you change the task over time, it would use previous experience for that. But maybe the main finding was that the PS implicitly discovered useful gadgets in this experimental context. So there were composite setups. A gadget is a composite setup of basic optical elements that were implicitly discovered by PS. So these were quantum optical devices that have been designed by humans with applications in state-of-the-art photonic experiments. And that was quite interesting because it was not something that was the proper task for the agents. The task, what was the protocol there, was we had an ensemble of agents, and their task was to find as many different entanglement classes as possible. The trick was there that newly found state at some point were no longer rewarded after some time, so they had to look for something else. After having, if you then select on successful agents and you open the memory of these, then you can identify highly ranked clips or connectivity in the memory, which then encode really these optical setups. So that was kind of a spin-off that it would be able to say from the memory structures what are useful gadgets in these types of experiments. Okay, another application number 3 that I wanted to present was in quantum error correction. Here the PS agent interacts with an environment which consists of a surface code, quantum memory subject to noise, and a classical control system that guides the quantum error correction on the memory and estimates logical error rates. Not much time to explain, but I would say similar as in the optical table experiment, the key ansatz was, of course, to map the problem to grid world. And here, you know, instead of an empty table, as in the optical table experiment, you start with a certain standard initial code, here a distance 3 surface code with 18 qubits, and moving around in the grid world, here corresponds to some basic code transformations. These are the actions that are done, certain code transformations that map the error correcting code from one surface code to a different one. And there's a certain notion of a code space that is big, and you have, if the requirement is find me a code that whose logical error rate is below a certain threshold, this is what I need, then PS will deliver this for you in a similar spirit as I talked before. Again, you observe there's a learning curve that you can see here, and there's also a notion of transfer learning. So that is was quite encouraging, and we could, the simulation were done up to 60 plus qubits, which corresponds to state of the art, you know, the more advanced quantum experiments on a mesoscopic scale. So more recently, let me just mention them. So we have applied it also to the automated design of quantum communication protocols. Very importantly here, there is also recent work. We have integrated PS with the deep neural network architecture, more precisely an energy-based model used for function approximation to update the age matrix. So similar to deep learning, deep Q learning, you can also create something called DPS learning, which is then you can inherit the methodology we are developing here for PS proper for larger action spaces and percept spaces. We also have a proposal how to integrate PS and other reinforcement learning in photonic chips, which I would just like to mention. So the summary here, we introduced PS as a physical model for learning agents based on stochastic processing of episodic memory. We tested the performance in simple task environments, for example, grid world, and in real world problems like robotics, experimental design, and other quantum information tasks. Now, yes, so these were a few applications where we first introduced the classical model, and we showed how this classical model of learning can be used in quantum experiments. Now, different from existing AI models, at least at the time we started this, the PS model also provided a natural route for quantization. And that is now really a different aspect where we don't look at quantized environments, but at a quantized agent. And I have, as I understand, hardly any time to go into this. So let me just say the basic steps. The basic steps were that you quantize the memory. The memory is the key notion of PS. So the task was to quantize the memory, which is the clip space, and clips are then states in a Hilbert space. And the classical random walk that we used for deliberation and decision finding in PS was the task was then to translate this into a quantum walk and use the results one has in the community for speeding up quantum walks, also for this learning model. So the idea was that, you know, can you establish that the agent can explore its memory in quantum superposition? Well, that's what we showed, that you can, in fact, and you will find a quadratic speeder then in deliberation and active learning. So I guess I have no time to go through that. Yeah, okay, I think that let me just say that I think technically the key point is that you translate this random walk in clip space into a Markov, describe it as a Markov chain, which requires a certain modification of in the description of the model. And then you use, having formulated the PS agent as a discrete time diffusion process over graphs, you can use some of the results and methods developed by people like Szigeti and other people who studied the problem of searching on graphs via quantum walks. That if you do this successfully, then you can connect the spectra of the walk operators in the classical chain and the quantum chain. You can connect them and you see that there's a quadratic scaling there, which is the origin of a quantum speedup for searching via quantum walks. And this can be then integrated into the PS model. If you want to know more about it, the theory paper is given here. We have also worked towards experiments. So there's a proposal how to do it in ion traps with superconducting qubits, and a recent paper has in fact first demonstrated on a simple system given a proof of principle experiments with trapped ions. So I'm now running really short and I don't know what to do. There is the last point would have been the fully quantized scenario where you have both the agent and the environment quantum mechanical. Let me just say this raises really several interesting questions. And one question is, what is here an action, such as a measurement performed by the agent on the environment, the basic primitive of quantum physics and quantum experiment. Here you quickly run into foundational issues like the role of the observer and the measurement problem. Another question is, how do you define learning in such a general scenario? In the classical domain, the notion of learning is usually based on the percept action-interaction history of the agent with the environment. You say, I saw this, and I did that, but that was bad, so I won't do it again. But in quantum physics, it's not so simple. To learn from past experience, one needs to know what has happened. So there must be some trace of what you did. If you have the system completely in a coherent superposition, you have to do some thoughts what to do. So this is really very interesting fundamental stuff. And there's a paper that addresses this problem and presents even an approach how to deal with a fully quantized scenario where you treat both actions and percepts as quantum systems that are exchanged between the agent and the environment. Right. And I guess I cannot say much more about it than pointing you to this PRL that is given here and subsequent work by Vedran and collaborators, where this is explored also regarding what notions of learning are there, how the history of the interaction influences possible speedups and so on. Very interesting paper just being advertised here. I guess my time is up. I wanted to talk about philosophical issues, but I'm not sure, Mr. Chairman. Do I have time for one slide, or how is it?
So I think we started 5 minutes later, so now you're definitely in the discussion part of the story, which is your part to do with it as you please. So I think if Bert agrees, we can do 2 more minutes.
Okay, then let me try to be quick. So because now I would come back to these initial questions that I posed. I think it's a fair question to ask more generally about the scope of machine learning for basic scientific research, beyond big data analysis, as you use it, say, in high energy physics or in observational astrophysics. What we have shown, to remind you, in the context of the photonic experiments was that a PS agent can learn to create setups of experiments that bring about a certain formally well-specified phenomenon, namely a certain type of entanglement. How can you create that? That was the question there, and learning agents can help you with that. And the key or the important feature was this gadget formation. That means interpretable structures in PS memory that helped us to reach that game. That was this gadget information thing was I think an exciting finding, at least for me. And I think it was an important step, but it is still far away from what we mean by genuine explorative scientific experimenting that we do when we do good experiments in the lab. Because there we are typically confronted with phenomena that are not yet fully understood. often we don't exactly know what we are searching for, as it was, for example, the case when people studied atomic emission spectra about 100 years ago. And they had to say, how does it come about that we see this kind of phenomena? And they started to construct theories for that. And understanding a new phenomenon means to identify relevant variables and building a physical model. And such a model, to deserve the name, should not only explain the observed phenomenon, but also allow you to predict the new outcome of new and unperformed experiments. And that notion of learning goes beyond the Bayesian framework of learning, as meaning updating some prior distribution of a fixed probability space. Here, the probability space itself, so to speak, is something dynamic, which has to be up for revision. What are the variables that play a role? How should I think about them? What degrees of freedom come into that? And I cannot discuss in any detail, but finally, I would like to mention just two recent papers that go a small step in this direction. One paper is on the learning of unobserved variables, which we did in a collaboration with Thomas Müller and Ben Ivar and Katja Ried at the University of Constance and Innsbruck. And that is described here in this archive paper. And another paper is on representation learning, which is a collaboration with Renato Renner and his group at ETH Zurich. Yes, and if you ask this question now, what have we learned? How will our research laboratories look like in the future? Can machines autonomously perform explorative experiments? Well, I think in the context of quantum physics, which is where I am at home, there are clearly several foreseeable applications which I talked about. There's clearly, you will have usage of active stabilization of large-scale quantum computers, where AI techniques really will be crucial, I think. It will be used for the control of complex systems, more generally speaking. You can use these in quantum communication protocols to find new and to optimize communication protocols, and in the design of novel quantum experiments. So it is, I think it's a clear something to be expected that we will have in the future something like research assistant systems. And these will be applications that clearly go beyond automated procedures that exist already in the laboratories, such as cooling, optical pumping, quantum state preparation. This is something more. It is of genuine, assistant level. And I think that the future role of AI in basic research will be of immense practical relevance due to that. But, and that would be the philosophical part, I claim that it will also impact our understanding of experiment. What is an experiment? Who and what is really the role of us in science? Yeah, so there are very interesting questions that are investigated in a collaboration with Thomas Müller and people in Constance that have to do with the question of the attributability and authorship in AI-driven experiments. Questions like who performs the experiment, what constitutes an experiment even. That is interesting philosophical stuff. And there's a collaboration that I want to advertise, and there will be also, several PhD positions in a research project that will be advertised soon. If you're interested in that, or if you know anybody interested in that, please point them to Thomas Müller or to myself. And with that, I think I'm really at the end. This is a list of papers. This is the people who have worked with me on the project in Innsbruck, and also people who have left. One of them is our chairman and other people here. Thank you very much for your attention, and thank you for
thank you, Hans, for this fascinating overview.